we're going to look at another triple integral, only this time the triple integral won't be over a box. So let's say that we're taking a triple integral over some volume W. Our density function in this case is just the function x plus y. Notice that there's no z in this function, but that doesn't matter. It could be that the density is just a function of the x and the y and not a function of the z as well. And we want to integrate this over our volume W, where W is the tetrahedron with vertices given by 0, 0, 0, 2, 0, 0, 0, 2, 0, and 0, 0, 4. So first, let's get an idea of what that tetrahedron looks like. I'm going to draw a sketch. And the x, y, z are 3. So we know the vertices of this tetrahedron. We have one right at the origin. We have another vertex where my x value is equal to 2. So I'll label this point 2, 0, 0. We have another where y is equal to 2, 0, 0. And finally, we have one along the z-axis at the point 0, 0, 4. So a tetrahedron, if you recall, is a three-dimensional object that has triangular faces, 4 triangular faces. So if I were to think of this as a solid, we would have one along the back wall in the zy plane, one in the zx plane, one in the xy plane, that would fill out to make sort of this triangular tetrahedron. It's not a box, it's a tetrahedron. So how do I integrate over something like this? Before, the bounds were really easy, and it's tempting to say that, oh, maybe my x values go from 0 to 2, my y values go from 0 to 2, and my z values go from 0 to 4. The problem is, if I were to trace out that much space, you would end up not with this tetrahedron space, you would end up with a rectangular box. And so we know that we have to limit ourselves so that we aren't going all the way out to each of the corners of the box. How do we do that? I'll tell you how. It's a two-step process. I'm gonna erase this so we have a little bit more space. So the hard part of these problems is setting up the region. The actual integration is usually pretty straightforward. So let's think about how we're going to set up this region. The step one for setting up a region is to pick a base. And I'm going to calculate this 2 ways, picking 2 different bases. But for this time through, I'm going to let my base be down in the xy plane. Visually, that's something that makes sense for me. So I'm going to think of this as the bottom of my tetrahedron. And then I'm going to think of the top of the tetrahedron as some function of x, y's, and z's. And in this case, the top of this is going to be the function that's the plane, right? We have this plane that's angling downwards. So once I pick a base, I'm going to find the bounds for this base. In this case, it might even be helpful to redraw what this base looks like. This base is in the xy plane, although I could have chosen it to be in a different plane. And I know that I have the point here where x equals 2 and the point where y equals 2. So the base, actually, we have practice at doing this. This is exactly a rectangular region that we've thought about doing from our previous work in the previous section. And in this case, we know that this line is given by y equals, what is that, 2 minus x. That's a slope of -2 and a y-intercept of 2. So if I were to set this up as a type 1 region, it means that I'm going to have my bounds on y go from 0 up to this function, y equals 2 minus x. So it means that my y values in this case are trapped between 0 and 2 minus x. Whereas my x values are going from 0 to 2. So why don't I have to trap my x values between 2 different functions? It's because the height at each place along here, I know that it's not going to go outside of this triangle because I've already restricted how tall the y value is. And so I know that my x values, as I travel from 0 to 2, my y values, or the heights along here, are already taken care of by this function. So we picked the bounds for the base, and I'm going to record them up here, just so that we can use them later on. Our bounds on y are from 0 to 2 minus x, and our bounds on x are from 0 to 2. So the next step that we need to do, once we pick the base, we need to come up with an equation for the top. Maybe I should put base and top, because spatially these things might change. So if this is our base, it means that we're looking down from a top view. It means that the top of this is going to be the height at every place along this base. And notice that depending upon where you are in the base, you're going to go up and hit different points along this triangular surface. And so the height in this case, maybe this isn't working because it's in 3 dimensionals, but is going to be this plane. So the top in this case is the plane that's cutting the top of the tetrahedron. And so we need an equation of this plane. We know in general that equations of planes, the easiest way, I'll tell you the tricky way that I would set up finding how this plane would work, although there are a lot of different ways. We have 3 different points on the plane, and as we've practiced in class, it's possible to come up with the 2 vectors that define the points from here to here and here to here, take the cross product of those 2 vectors, and that'll give you a normal vector, and then we can plug in one of those points. All of those steps will give you the equation of this plane. But I bet we can do that a little bit faster this time. I'm going to do it by guess and check, because I see that there's a really clear relationship, 2 and 2 and 4. I'm going to set it up so that some coefficient times x plus some coefficient times y plus some coefficient times z has to be equal to 4. I'm picking 4 because I know that each of these intercepts are multiples of 4. So just by cleverly, without having to do a lot of mathematics, I can see that if both the y and the z are equal to 0, when I plug 2 in for x, 0 in for y, and 0 in for z, I would want to get out a 4. So that means that my coefficient on x would have to be a 2. Similarly, the coefficient on y would have to be 2, and my coefficient on z in this case is just equal to 1. And I could check to make sure that this formula actually works by plugging in my points. So 2 times the point 2, 0, 0, 2 times 0 plus 2 times 0 is in fact equal to 4. So I plugged in the point 2, 0, 0. Next, I could plug in the point 0, 2, 0. Oops, this should have been just 0. The coefficient on my z is just 1. And this again gives me 4 by plugging in the point 0, 2, 0. And then finally, I could plug in the point 0, 0, 4. And I see that 2 times 0 plus 2 times 0 plus 4, in fact, gives me 4. So this is my shorthand way, given these 3 easy points, to be able to come up with the equation of my plane. So now that I have an equation for the top of this surface, I also need an equation for the bottom. And in this case, we have bounds on our x value, we have bounds on our y value, so this is going to need to be a bound on our z value. So my equation for my plane is given like this. I'm going to solve it in terms of z, and I find that z is equal to 4 minus 2x minus 2y. This is the top of my plane, and I know that it goes down until I hit the xy plane, so the bottom bound is where z is equal to 0. If I wanted to write this out in the same notation that I had before, it means that 0 is less than or equal to z is less than or equal to 4 minus 2x minus 2y. So I've tracked the heights here going from 0 up until I hit this plane. And I'm only going to calculate it for the points for which I'm within this rectangular region in the xy base. So now I have all my bounds. we can actually set up our integration. These bounds, oh, I shouldn't be writing it green, and these bounds together work together to set up my integral. And the integral in this case, I guess I'll erase something here. We have the bounds for our z, we have the bounds for our y, and we have the bounds for our x. And those bounds are going to be exactly the bounds on our triple integrals. The only problem is, maybe I should put this as my step 4. Are we on step 4? I need to make sure that I do them in the proper order. And what do I mean by proper order? I'm setting up a triple integral over this function x plus y. I have to be careful about whether I go dx, dy, dz. I'm going to see what happens. If I start with my bounds on x, it means my innermost bounds are going to be from x equals 0 to 2. My next bounds are going to be from y equals 0 to 2 minus x. And my last bounds are going to be from z equals 0 to 4 minus 2x minus 2y. I'll see why this is a problem. This ends up being a problem because when I actually go about integrating this, maybe I shouldn't have erased all that, that's okay. When I actually go about integrating this, I can take this integral with respect to x, I plug in the bounds, all of my x variables will go away. But then when I integrate with respect to y and plug in these bounds, I'm reintroducing my x variable. And it means that I don't want to have x's in my final solution. I want to just get a number. I want this to be a number in the end. And so having variables on my outermost bounds are bad. I'll write that down. And maybe I'll have you step through this in your homework, that if I actually were to go step by step and do this integration in this order, my final solution would have lots of x's and y's in it. And that's not really what we're looking for. So instead of integrating in this order, I'm going to integrate so that each subsequent outer integral has fewer and fewer variables. So my first, the z bounds have the most number of variables. And in general, your top function is going to have the most number of variables. So I'm going to flip this around so that my z variable is what I'm evaluating first. And then the bound that has the next most number of variables is my y bounds. And then the last one will be my x bounds. And in general, I should say that we always want constant terms. Maybe I should say constant bounds of integration on the final integram. Meaning the last time that I integrate, I want to make sure that these bounds are constant terms so that when I finally plug them in my last step, I'm just left with a constant. So now that we have it set up, actually the rest of this is just easy. We're going to do some integration. So let's go ahead and do some integration. It will be sort of computationally messy. And if you don't want to see the computation, you can go ahead and just stop this